Now coming to the famous diagram, that is Darrow Yannet diagram. What is this Darrow Yannet diagram? It compares what happens to the body whenever we add some substances in the ECF or remove some substances from the ECF. So before going into it, we should understand one concept. Suppose what we are trying to manipulate is we are trying to manipulate the ECF and see what is happening to the ICF. So if we add many substances which are isotonic in the ECF, do you think will there be any movement from ICF to ECF? The substance added is isotonic. Isotonic substances does not cause any movement. So what will happen? It will stay in the ECF only. So there is no movement whenever isotonic solutions are added to the ECF. Next comes the second concept. Suppose we are adding a hypertonic substance. Suppose you are adding a hypertonic substance. What it will do? This tonicity or the solutes which are more, they will drag water from the ICF. So this is very important to remember. Hypertonic solution, they can drag water towards it. They can take up water. If we add a hypotonic solution, suppose a solution is there where you add a hypotonic solution, what it will do is the tonicity on the ICF will be more now. So ICF, they can drag water towards it. So this is the one concept that you should remember. We'll revise it back. The isotonic solution, there is no movement. Hypertonic solution can take up water. Then hypotonic solution gives away water. So if you know this concept, then the Darrow Yannet diagram is easy to remember. So first, we have to remember the normal diagram. What is given along the x-axis? Given along the x-axis is the volume. As you can see in this diagram, ECF is more or ICF is more? ICF is more. So there is more space given for the ICF. This side is the ICF where more volume is given. Here the more volume is given for the ICF. Whereas the ECF volume is less because as is the ECF itself is less. This is a normal diagram. And along the y-axis there is osmolarity given. And remember one thing, in the body, it will always try to maintain the osmolarity constant in between the ECF and ICF. So at the resting stage also, both of them will be similar. Suppose if you try to add any other substances also, ultimately the final after equilibrization, the osmolarity will be equal for both ECF and ICF. This is an important point to remember. The osmolarity of ECF and ICF will reach an equilibrium. This is important. So now let's get into adding some fluids into the ECF. So first coming to isotonic fluid. We are just going to try and add an isotonic fluid. What will happen? Suppose if you add an isotonic fluid to the ECF, will it move to the ICF? The answer is no. So just the volume of ECF will be increased. This dashed new lines will be our end point. So at end nothing will change except that the ECF volume becomes increased. So what is happening here is, the example here is addition of 0.9% NaCl. So whenever a patient comes to me and we just want to increase his ECF volume to increase the circulatory volume or to increase the perfusion pressure, we just will be giving an isotonic solution, that is 0.9% NaCl. So ECF volume is increasing. All of this will be mirror images. So if we remove an isotonic solution, what will happen? There will be a reduction in ECF, nothing will happen to the ICF. So the classical examples are vomiting and diarrhea in the initial stages. Later on, more losses of electrolytes can be there which can alter this. But initial stages, vomiting and diarrhea, they will just reduce the ECF. Nothing else will happen. They will just reduce the ECF. Now coming to the addition of hypertonic solution. So hypertonic solution, what did we see? Whenever hypertonic solution is added, it can take up the water. So first thing is addition. You go for an addition. We are trying to add an hypertonic solution. First tell me what will happen to the tonicity. The tonicity will definitely increase because ECF tonicity is increasing. So ICF tonicity also will increase. So what will happen? The tonicity first we will draw. The tonicity is increasing. And we are adding it in the ECF. What is the property of hypertonic solution? Its property is to drag water towards it. So the ECF volume will increase. So we have increased the tonicity and it is taking water from the ICF. Suppose ICF, from the ICF it is taking water. So what will happen to the volume of ICF? ICF volume has to contract and come into a new lesser state, but their final osmolarity will be same to same. So now we will remove the hypertonic solution. How will you remove the hypertonic solution? What is the example? Now the example for adding hypertonic solution, we forgot to mention, it is 3% NaCl. That is a hypertonic solution. Then removing an hypertonic solution. What is that? So basically we have to remove more of salts. There is an example called as aldosterone insufficiency. What does aldosterone do? It takes up the sodium. If the aldosterone is insufficient, what will happen? There will be increased loss of sodium. Whenever there is increased loss of sodium, what will happen to the tonicity? First, we'll talk about tonicity. What will happen to the tonicity? The tonicity is going to come down. So, if the tonicity is going to come down, it becomes hypotonic. So, first thing is, let's draw the tonicity here. It becomes hypotonic. Then what happens? If the solution is hypotonic, it will give water to the other side. Here we are withdrawing it from the ECF. So, it will give its water to the ICF. So what will happen to the ICF volume? The ICF volume is going to increase, whereas the ECF volume is going to decrease. So as you can see here, these two are again the mirror images of each other, because one we are adding hypertonic solution, another one we are removing hypertonic solution. So coming to the third one, that is hypotonic addition and removal. So what happens whenever we add an hypotonic solution? Hypotonic solution, all of us know, it is giving water to the other side. So first thing is, whenever you add a hypotonic solution, what will happen to the tonicity? The tonicity is going to come down. So first thing is, we'll draw the tonicity. That is, the tonicity is going to come down. So whenever this is coming down, now from where it will drag the water? From the ECF, it will drag water to the ICF, because we are adding a hypotonic solution. So from the ECF, it is going to drag water and give it to the ICF. So what is the classical example? Is the SiADH. Here hypotonic solution is added, and it is adding water also. It is adding more and more water to it. But one funny thing that happens here is, the water molecules, it gets more added to the ECF also. So relatively the ECF volume was also trying to increase here. The osmolarity has come down, the ECF volume is also increasing. Since it is hypotonic, more volume is shifted to the ICF also. So both ECF and ICF is increasing in this condition. Then what will happen whenever you remove the hypotonic solution from the ECF? Let's see. First example here is, there is a classical example of diabetes insipidus. Here there is just water loss. There is no solute loss. Here the water is getting lost. So whenever the water is getting lost, what will happen to the volume? The volume is going to deplete in the ECF. Whenever there is volume depletion in the ECF, the osmolarity is going to increase. First thing, we have to start here with the volume depletion. So ECF volume is getting depleted. Since the volume is less, the number of solutes compared to that volume will be more. So the osmolarity is going to increase. Now initially the fluid will be sent from the ECF, but later on stage, what will happen is, it will be dragged from the ICF also. So ICF volume also contracts, but both the osmolarity will reach a new equilibrium. So this is the Darrow Yannet diagram for the hypotonic addition as well as removal. Hypotonic addition as well as removal. And as you can see here, they are both again a mirror image of each other. So once you know the one concept, you can go and correlate it with the other. In this, we have to remember that there is addition of water and there is removal of water in case of hypotonic solutions. The classical examples being the SiADH and the diabetes insipidus.